Okay, we'll get to what might be my final video on the Rayleigh distribution. Um, what if we don't know that parameter sigma in the PDF? Here's the PDF, probability density function of the Rayleigh distribution. It's all determined by the shape of it's completely determined by the single parameter sigma or sigma squared. It looks, these are different PDFs for different sigmas. Okay, what if we don't know that? We're going to use maximum likelihood estimation. You might want to look this up on your own. You look at my website, my random processes and element filtering course covers it a little bit. You define a likelihood function, and it's really a joint PDF conditioned on that parameter. Since we don't know what that parameter is, it's kind of a conditional probability or a conditional likelihood. This chi here is actually a bunch of measurements. Is that chi or z or something? But it's actually a bunch of actual measurements. The idea kind of, if you actually did a bunch of experiments of mist distances, threw a bunch of darts, and you did a histogram of your mist distances, well, they might look kind of like one of these distributions. If most of your mist distances were down here around a half, say from 0 to 1 or so, you'd probably say, well, it's closer to this blue guy. Sigma equals a half. If they grouped more around 2 here, say between, I don't know, 1 and 3, you might pick this red guy. Sigma equals 2. These shapes hopefully will match. You want a good match with your histogram of measured data. That's as much as I can try to explain it intuitively of why this makes sense. We're going to additionally assume that the measurements are independent so that this joint PDF, like this, is the product of the individual PDFs. Since we're assuming they're Rayleigh, it's this product here. So we want the sigma or sigma squared that maximizes this likelihood. Well, the way to go about doing that is called the log likelihood method. And because the natural log is monotonically increasing, if I maximize the log likelihood of that product, I'm maximizing that product. So in log, all these terms, the product of terms become the sum of terms. So we'll take the sum of each of these individual logs, each log of each of these individual terms. And what's the log of this guy? It's the log of r sub minus the log of sigma squared minus all this. It's that. And then how do we maximize? We just take the derivative of this guy and set it equal to 0. Take the derivative, set it equal to 0. The derivative of this guy with respect to sigma squared is 0. Sigma squared isn't involved in this term. With this guy, it's 1 over. That minus comes down. Derivative of natural log is 1 over. And this guy is just, we're treating sigma squared as the parameter. So it'll be a sigma fourth in the denominator. Hopefully you can follow all that. Multiply through by sigma squared and split it up. You basically get a sum of 1 from 1 to n, which is just going to be n, equals this guy over here. Anyway, you do that little bit of algebra, you have a formula for sigma squared. It's this guy. Call it the sample. It's not the sample variance. It's the sample sigma squared. Now we could put that into the Rayleigh distribution here or in the CDF and make all the computations we otherwise make. That's, I think, as far as I'm going to go, at least for now. with the Rayleigh distribution. Those of you bored by everything else.